Ah yes, I see here that you have been diagnosed with can't integrate. Oh, that's a pretty serious condition. Nonetheless, why don't we go ahead and go over from the very beginning all the steps about integration so that you can now finally study and practice for the AP exam that's coming within the next few months. I can't say I'm surprised though, but you've come here and now we finally get to be together to go over all the things you need to know to integrate. So to actually begin, we will need to understand the actual definition for integration. And so if we were to start with an integral of the function f of x of d of x, then we actually end up with a result, a new function called capital F of x plus c. And so with the starting function taking an integral, you will then receive a new function. But what happens from there is that we need to say an if statement here. If we actually know that this is the integral, then if we go ahead and take that new function that came out, capital F of x, and we take the derivative of it in respect to x, we will end up with the starting function f of x. And so from here, if we go and realize that the new function that results with its derivative goes back to the original function that was inside of the integral from the start, we have indeed checked to make sure that this is the correct integral that resulted from our operation. And so for what we're going to do here is that we have a number of different integration rules all listed right there with all the different rules that we will go over together in this new series. And so what we're going to have to do is go over each of those rules with some example problems, and hopefully from there you should be able to begin integrating on your own. And so we'll go over some rules today. Let's do the first one, something that I like to call, if we were to list it out over here, our first rule is the coefficient rule. So this rule is, I would say, one of the most simpler of the rules. And so if we were to really write it out, if we have a new integral with a coefficient k multiplied into the function of x of d of x, the coefficient rule comes in handy because what we could do from here is that instead of integrating all of that together, we take that coefficient k and we throw it right outside of the integral. And so that result will turn into the coefficient k multiplied on the outside of the integral f of x dx. Pretty simple. I hope so, because from here, this can actually help us quite often and a number of times to make our integrals a lot simpler. Again, the whole point is that you'll integrate the f of x dx on itself, and then you'll multiply that coefficient afterwards. Now, hopefully from there, we should be able to go onwards to the second rule. The second rule for integration is something that I'd like to call the addition rule. And so the addition rule comes in handy in a number of different ways. So let's go write out what this looks like. And so with the addition rule, we will now have instead two functions. We have the integral of f of x plus g of x, all inside of the integral of d of x. And so what does this look like is that with addition rule, we will quite literally go up to those two functions and say, I get half. And then from there, you will split that right down the middle into two separate integrals. We have f of x of dx plus the integral of g of x dx. And we end up with something like this. This is quite useful because you are now integrating instead of one big integral, you have been separating it to f of x being integrated first and then g of x being integrated second. A different way to visualize this is that f of x is coming up to g of x and it's going to say, Mom said that it is my turn for the integration. And so it will get integrated first, g of x gets integrated second, and the addition will happen after the fact. Pretty useful, I would say. Feeling pretty good? Well, let's go over the third rule and then into some practice problems. Oh, what rule is this? That's way too complicated. Oh, we can't do this anymore. Shut it down. I can't. This is too complicated. Oh, after all this time, we just have to give up. No, absolutely not. We are not giving up after the third rule. This is the exponent rule, one of the most important rules for us to learn in our time together. And so I'm sure you are quite confused with all of this that's going on here. And I'm pretty sure your reaction is going to be something like this. Oh, what is all that? There's not even a single x in there. Look, there is a u and an n and a du and all this business right there. What does it even mean that n cannot be -1? This is too much. We can't do this. We're so cooked. We are not giving up like that easily. So instead of complaining all day long about how complicated this rule is, why don't we actually go ahead and start dissecting this in ways that we can understand and ways that we can continue to use and practice. This is a rule. This is the generic way of actually writing out what happens from this type of integration. So why don't we actually rewrite this in terms that we do understand and see if that example can help us visualize what goes on from this rule. So let us make a new integral instead with easier terms, something like x to the third power dx. Oh, those are some terms in which we are much more familiar with, aren't we? Yes. So from there, why don't we go lay down the actual rules to make sure we're on the same page about what each different part now represents, starting with u being equal to our new x that is in the integral, and n being the exponent is going to be 3. Pretty good. And so from there, we have the last things that we need to truly write down here for our terms is the n plus 1. Oh, would you look at that? N plus 1 is simply 4 in our example. All right, pretty okay. And so now we can actually solve this integral in much easier terms because we follow the rule. We take our u, which was x, our n plus 1, and the exponent, which is just 4 now, adding 1 to the exponent, and a new denominator of that same exact n plus 1 of 4, and a plus c after the fact. Now, I know many of your teachers back at home are very big sticklers about that plus c and get all over your cases about that issue. I'm going to be the same, if not even worse, if any of my students forget that plus c. If you do, you're doing your indefinite integrals incorrectly, and you deserve to get no points if you do not add that plus c at the end of it. Believe me, this is a lot more where that came from. And so, one thing that we might have an issue with is that how do we even know that this is even the right answer? Am I just spouting a bunch of nonsense just so I can get views? Maybe, maybe not. So, what is the way that we can check for integrals being the correct answer? If only we went over the very definition of integrals first. That given that this is a resulting capital F of x that came out of our integral, well, if we just went ahead and took the derivative of our answer, shouldn't we return back to our starting function? Oh, if only someone could rewind back in time to get back to what I wrote down from the start. But wouldn't you know that that is indeed every way in which we can check an integral is we simply take the derivative of our answer and we should return back home to our starting function. So why don't we do that? Let's go ahead and take that answer, x to the 4th over 4 plus c and see if this derivative, so all of this guy, taking its derivative in respect to x, would indeed give us our function back again. Well, what do you know?
But I don't know how to do derivatives.
That's not my problem right now if you can't integrate, nor differentiate. My problem right now is making sure we can check this properly. So, if you simply cannot follow along with differentiation, we have another topic to discuss at a later time. But for now, with this current check, we'll just assume that you can differentiate. So, the rule that we will utilize here, being that it's x to the fourth over 4, we will have to use the differential power rule. Pretty nice rule for us to follow along with. In that, we will then take the exponent of 4, bring that down in the derivative, and then subtract the exponent by 1. What this will look like is we have 4 coming down multiplied by x to the third power all over 4. Those don't stay the same. The derivative of any constant number, and that's just any number that we haven't found out yet, but a constant number, that simply goes to 0 when taking a derivative in respect to x. All right, cool. So now we can simply cancel out the 4 on the numerator, 4 on the denominator, and oh man, would you look at that. We ended up with the same exact function, lowercase f of x, as we started with in the beginning of our example. Oof, that's some pretty spicy math if you ask me. Now, I think this really does check out that we did integrate properly, using the very basic definition of integration at the first steps of our lesson here. Looks like we're just about ready for some practice problems. So we'll transition into some of those. We'll try to see if we can follow along with the way to solve them. And I think we should be pretty good for these first 3 rules of integration.